All right, guys, I want to start working with, we kind of finished yesterday with it, but we didn't get very far, the double angle formulas. Okay, so a double angle formula is exactly what it says, a double angle. So you're multiplying something by 2, right? So your argument's going to be like 2x or 2 theta or 2 phi or whatever, okay? As we progress through the day, through the period, you're going to find out that if I know, if they're asking me what the cosine of like 3x is, I can rewrite that as a sum of 2x and 1x, right? And then that 2x is a double angle, okay? The 2x plus 1x ends up being a sum difference formula. So what we end up doing here is intertwining multiple formulas to be able to kind of break something down, okay? So here's kind of, we're going to go through the sine function here, the sine double angle, work through it, see what its formula is, and then talk about why it's useful for us, all right? And then that will then be kind of the logic of why the other ones are useful for us, and the process that we go through today are going to be useful, okay? So here's the idea. We know that the sine of 2x is the same thing as the sine of x plus x. Would you guys agree with that? And if I know the sine of x plus x, that is a sum formula for sine, right? And the sum formula for sine looks like this. Sine of the first angle, cosine, second angle, same sign, and then cosine first angle, sine second angle. But first angle, second angle are the same, right? So we just fill those things in. And now you have sine x cosine x, sine x cosine x, right? So you should have 2 sine x's cosine x. Okay? Which now that is the sine of 2x. And what that does, it says, okay, well, what if I'm interested in finding the sine of, let's say, 60 degrees? Well, you know that that is the sine written as a double angle 2 times 30 degrees, right? Does that make sense? And now you see that that 2 is the same as that 2, and the 30 is the same as the x, right? So now I can go through and say, okay, well, 2 sine of 30 cosine of 30. So this is basically telling me that the sine of 60 can be determined by just knowing the ordered pair of 30 degrees. What is the cosine? Or sorry, let's do the sine. What's the sine of 30? Yeah, that's going to evaluate to 1/2. What's the cosine of 30? Radical 3/2. When I multiply those together, that gives me 1, right? Is that the sine of 60 degrees? Absolutely. Okay? And you can do that then with any measurement you want. Okay? Think about any unit circle number, 120. It'd be 2 times 60, right? If I wanted 180, it'd be 2 times 90. If I wanted, you know, what? Well, I think we've kind of addressed all of them. If we take any angle that we want, and it can be written as 2 times something else, we should be able to use this formula to generate it. Now, the thing is, the sum and difference formulas, you think about what they did for us. Okay, we knew the unit circle. We knew around the unit circle multiples of 30 and multiples of 45. Okay? And the sum and difference formulas allowed to generate new ordered pairs off the unit circle that we did not already know. They gave me the 15-degree angle and the 75-degree angle, right? And all the multiples or symmetries across the unit circle of 15 and 75 degrees. Well, now take 15 and double it, you get 30, right? So that's not new. 30 is not new. Take 30 and double it, you get 60. That's not new. Okay, take 45 and double it, that gives you 90. That's not new. 60 and double it gives you 120. That's not new. 90 double it gives you 180. That's not new, right? 75, double it, that's not new, 150. Okay? So what happens with the double angle formula, you don't generate anything new off the unit circle, any new locations. Does that make sense? So you might think, well, this is pointless. I've already got ways of finding these things that might maybe seem simpler. Okay? The benefit of this here is when we get to equations, and I give you this question here, I give you the sine of x equals the sine of 2x. Okay? And we want to solve that equation. And I'm going to work through this here with you. I'm not saying you need to learn how to do this right now. It's going to be, I think, section 7.4. We start learning about solving equations. But this is the purpose of this. So I want you guys to kind of foreshadow a little bit and see where we're taking this stuff so then it makes more sense to you now and why we got to learn it. Okay? And it becomes more important to us now. So sine of x equals sine of 2x. If I were to graph those, we know, hopefully, from what we've learned in Algebra 2, Algebra 1, college algebra, that the answer to that question is simply where those two curves intersect, right? Okay. Now for us, they're going to intersect in an infinite number of spots because of the periodic behavior of these things. So let's maybe just restrict this to 0 to 2 pi. Same thing here. So what we go through here in a moment is going to find where those shapes cross. And how many times do they cross? Once, twice, 3 times, 4 times, 5th time, right? Okay, but this 5th time is the repeat of that one. Does that make sense? Okay, so when we go through this, we're only going to find the 4 different values, the 4 different intersections. Okay, so what we learn, what we find out is that you cannot solve an equation like this when the arguments are different. Okay? So what we need to do is we need to either increase this one somehow, and I'm going to tell you can't do that, but you can depreciate this one. Okay? So we're going to rewrite this as the right-hand side. We're going to write it as, it's a sine double angle. So we're going to rewrite it as that. 2 sine x cosine x. Okay? Now, what's going on here is this is if I view like sine x is equal to u, and let's say cosine x is equal to r. Just choosing arbitrary values here. This formula here down here, this equation would look like u equals 2 ur. Can I subtract u from both sides? So if I was doing it algebraically, it'd look like this. 0 equals 2 ur minus u, right? What can you factor out of both of these? U. So that gives me 2r minus 1, right? Okay. Well, that would mean, if that's a product of objects, that means u is equal to 0, and 2r minus 1 is equal to 0, right? And I can go 2r equals 1, r equals 1/2, right? And u was 0. Well, let's think about what was u? It was sine of x, right? Sine of x equals 0. What was r? Cosine x. That equals 1/2. Okay, that's one way of doing it. I like that technique, but a lot of people won't use that. We'll just do this. We'll go, okay, I'm going to remove the sine x from both sides. So it looks something like that, right? And then they say, okay, well, these are 2 terms over here. They both have sine in them. So they factor that out. That would have been the process of factoring that u out. So I get sine of x times the quantity, then 2 cosine x minus 1. Again, this is a product of 2 objects, and they equal 0, so we've got the 0 product property. So we say sine of x is 0, And 2 cosine of x minus 1 is 0. Solve both these for the trig function that's left over. So this would be 1/2 equals cosine x. And this would be 0, obviously, equals sine x. And that's exactly what we have here, right? Now we ask ourselves, and we would use inverse functions, but because of these numbers that are convenient, and we should know these off the unit circle, what angle measurement, and give it to me in radians, what angle measurement is the y value, because that's what this is, right? That's the y value off the unit circle. Which angle gives me a y value off the unit circle of 0? 180, right? And what's the other one? 360. Now, 360 one I'm actually going to write as 0. So 0 degrees or 0 radians. And now 180 degrees or pi radians. Those are the 2 spots that the sine function is 0. Okay? Now cosine, so when you said 2 pi or 360, that's that 5th answer that is the same as that one. Okay? Cosine, what angle is cosine 1/2 for on the unit circle? Pi over what? Pi over 3. Okay, so we're looking at, so on the unit circle, pi over 3 would be right there. That x value is 1/2, right? Isn't the x value also 1/2 down here? Does anybody remember what that is down there? Well, think about this. This would have to be pi over 3, right? Not 7 pi over 3. 5 pi over 3. Okay? So that's, and with that unit circle, guys, that's going to be, it's going to be important to us again here pretty soon. But let's think about these answers. If I were to graph, come back to this graph, we said one answer was x equals 0. Would you agree on that line, those 2 graphs intersect? We said one answer was x equals pi. Do those graphs intersect at pi? We said x equals pi over 3. Do those things intersect at pi over 3? And x equals 5 pi over 3. Do those intersect there? And if we said 2 pi, that's the repeat of 0. Okay? So what we end up with then is the ability to solve equations that have multiple angles, okay, inside their argument if we can break them down so that they have one angle or one coefficient for their argument. Does that make sense? Okay, so that's the benefit that we're going to, the largest benefit that we're going to see of knowing these particular double angle formulas. Okay, so that's the sine formula. Now, I want to do cosine. All right, so the approach is identical. I'm going to start with cosine of 2x. That's what I'm trying to solve a formula for, create a formula for. We know that that is the same as cosine of x plus x. It's the same exact steps we do with the sine, right? Is that a sum formula for cosine? And that turns into cosine of the first angle, cosine of the second angle, opposite sine, and then sine of the first angle, sine of the second angle. Okay? Now the angles are all x. What does that generate for us? What would you rewrite that as? Careful. Cosine squared x. And you write this as sine squared x. And that is a version of the cosine 2x. I say it's a version because we have some identities here that we can substitute to alter it a little bit. Okay? This is the nice thing about, it's kind of it's a nice thing, but it also stinks, okay? Because with like the sine double angle, you have one and only one formula, right? And that's the nice thing about it. That's the nice aspect of it. But that double angle formula for sine, when we expand and get 2 sine x cosine x, it incorporates both sine and cosine, right? It incorporates 2 trig functions. This also, when we write this way, incorporates 2 trig functions, but we can kind of eliminate that. We can eliminate one of these because don't we know this identity here. Okay, so I can say that the cosine of 2x is equal to, let's replace cosine squared. If I replace cosine squared, wouldn't it be with 1 minus sine squared x, right? And then minus the sine squared here. Okay, so that's that. So doesn't that give me 1 minus 2 sine squared x? There's another version of your double angle formula. What's nice about that, think about this, if I want to find, using the blue one, if I want to find, let's say the cosine of 60 degrees, that blue one is saying you need to know then the cosine of 30 and the sine of 30. And that black one, if I want to find the cosine of 60 degrees, it's saying all you need to know is the sine of 30. Okay? And he eliminates you having to know an entire point off the unit circle. Which, is that useful to us? It shouldn't, because we should know all those points, right? Okay? But it is, in regards to solving equations, it is going to be nice to maybe be able to get rid of the cosine. And if I solve cosine 2x, it might be nice to get rid of that and bring in a sine. Okay? There's another way of doing this. It's in red. Cosine of 2x. Starting with the blue one again. I can write as cosine squared x minus, now isn't sine squared going to equal 1 minus cosine squared? Does that make sense to everybody? Okay. Now just be careful because it's minus a quantity. So it looks like cosine squared minus 1 plus cosine squared. So it actually ends up being 2 cosine squared x's minus 1. And that's a third version of your cosine double angle formula. So I want to go through an example of using that and kind of see the varying benefits of knowing either Formula 1, Formula 2, or Formula 3. Let's say that we have the task of finding the cosine of 60 degrees. Now, again, this formula, because of the double angle aspect, isn't going to produce anything that we don't already know off the unit circle. So we should already know this gives me 1/2, right? Okay. But if I'm tasked with finding this using a double angle, I think the best thing to do is to rewrite this as cosine of 2 times 30 degrees. Because now that tells you what your x is throughout the entire thing, right? Okay. So if I'm going to use this blue, I'm going to use formula number 1 here. We can rewrite this as cosine squared of 30 degrees minus sine squared of 30 degrees. And I think some people are probably going to prefer maybe seeing it this way. Remember, that's what squaring a trig function really means to us, right? When we write it this way. So what is the cosine of 30? Radical 3 over 2. I'm going to square that. What is the sine of 30? 1/2. We'll square that. What's radical 3 squared? 3. What's 2 squared? 4. Minus 1/4 gives me 2/4, which is going to simplify to 1/2. Is that exactly what we knew cosine of 60 should be? Yeah. Let's go. Let's do it again. Let's go. Cosine 60 equals cosine of 2 times 30. Well, let's use that formula there. Formula number 2 here. This would be 1 minus 2, and it'd be sine of 30, that squared, right? Does that make sense? It's 1 minus 2. What's the sine of 30? 1/2. And we're going to square that, right? So 1 minus, what's 1/2 squared? 1/4. What's 1 minus 2 times the 4th? 1/2, right? 2 times the 4th is 1/2, so 1 minus 1/2. It's 1/2. Okay? Kind of sounds like maybe we need to do another unit circle quiz. Okay? Sounds like we're struggling with that stuff. Okay? But remember, that's like if I was going to give you a 5th grade math test and you didn't know how to add or count or subtract or multiply or divide. You wouldn't be very good on that 5th grade math test, right? So on a trig test, you're not going to do very well if I don't give you the unit circle. And you have to recall that unit circle, right? Does that make sense? Okay, and that's going to happen here pretty soon, Chapter 7. I'm not going to give you any of the unit circle, and you got to know that. Okay? So, we could do the same thing then with that red one. I'm not going to spend time. We go 2 cosine of 30 squared minus 1. So 30, cosine 30 is radical 3 over 2, right? Square that, you get 3 over 4. So I get 2 times 3/4 minus 1. Okay, 2 times 3/4 minus 1. What's 6/4? Which is 3/2, right? 3/2 minus 1 is 1/2 again. Okay, so you can use any one of those 3 formulas to generate the cosine double angle. Okay, now let's kind of address why maybe this would be a useful task for us. Okay, we did this in the last class. Okay, it says rewrite cosine 3x in terms of cosine x. Now the reason I would want to do this, so let's kind of play this game here. If I go cosine x equals cosine 3x, let's say we're a week out from today and we're solving that equation. Just like I showed you with the sine of x equals sine of 2x, you can't have varying arguments, right? Okay. Now, graphically, obviously, it's no challenge graphically. I can go cosine of x and then cosine of 3x, and we can get those answers. Okay. So we'd be looking at, let's restrict all of this between, let's just do this. Let's go 0 is less than x is less than 2 pi. So we're looking at all the intersections in that blue region, right? Does that make sense? Okay. So we got 1, 2, 3, 4, again, 5 answers, one of them being a repeat, right? Okay. I want to go through the process that would allow us to just get into a situation where we can start solving for those spots. So this is how we do this. Cosine 3x, that is not a double angle, right? That's a triple angle. A lot of times once we go over double, we just call it a multiple angle. Okay? But every multiple angle can be rewritten as a sum of 2 smaller angles, right? So cosine 3x can be rewritten, let me write this way, cosine 3x, hang on, let's do this, as cosine x plus 2x. Do you agree with that? Or if you want to go 2x plus x, it doesn't matter. It's commutative. Okay? Now, why is that useful? Why does that benefit us? That's a sum rule now for cosine. So doesn't that look like this? Cosine x, cosine 2x, minus sine x, sine 2x. Is that appropriate? Okay. Now, this cosine x is going to be cosine x. And I'm working through this in regards to trying to write things with cosine only. So now I get to this step right here. And I want to make a substitution. I have 3 things that I'm able to substitute there. I'm able to substitute cosine squared x minus sine squared x. I'm able to substitute 1 minus 2 sine squared x, or 2 cosine squared x minus 1. And that's the one I'm going to use. I'm going to replace this with 2 cosine squared x minus 1. You have a choice of any of the three, and based off the directions in this problem, and ultimately, when we get to the equations, kind of having this in the back of my mind that I want, as much as I possibly can, to have all the same trig functions, I'm going to try to use the 2 cosine squared x here, minus 1. Okay? Is it okay with everybody? Then it's going to be minus sine of x. And now this here is a sine double angle, right? So that thing is the 2 sine x cosine x. Now we just go through the algebra that's being presented here. You have a value here and a binomial there, right? You have a monomial times a binomial. You have to distribute. So I get 2, it'll be cosine cubed x minus cosine x. Okay? And now this is going to be multiplied by that, so it gives me minus 2 sine squared x cosine x. Is that right? So if my only task was to get rid of all the 3 x's, to get rid of all multiple angles in the expression, we've done that, right? Every argument here is now 1x. So that's good. That's kind of the benefit of these rules. Okay? Now there's the additive task of making sure everything was written in terms of cosine. So don't I need to go through and somehow remove that? So that is going to be removed by knowing that. Now I'm going to use the, so I can group these two, right? 2 cosine x, and then the sine squared x is actually 1 minus cosine squared x, isn't it? Okay. So then 2 cosine cubed x minus cosine x minus 2 cosine x plus 2 cosine cubed x. How many cosine cubed x's do you have now? 4. And you have minus 3 cosine x's. Does that make sense to everybody? Okay. That's a tedious process, but that just shows us that cosine of 3x can be rewritten in terms of cosine of just x. And if we, let me just get a new window up here. So if I were to just graph cosine of 3x and then 4 cosine of x cubed minus 3 cosine x, you see on the right hand side that those two curves are the same, right? Okay. So that's nice. Now let's see how that helps us with this overall equation that we were interested in. So in order to solve this initial equation, we would have had to transition that side, which we've done. Let's just take this side down here now and write it right there. Cosine x. This is now just a, if you think about it, it's an algebra question, college algebra question. Let's say cosine of x is equal to u. Would this be u equals 4u cubed minus 3u? And what would you do to start solving that? Subtract u, so you have 0 equals 4u cubed minus 4u, right? And then you'd factor that, right? And you'd have 0 equals 4u times u squared minus 1. And that would give you 4u equals 0, u squared minus 1 equals 0, Okay? So then that would be, u squared minus 1 is going to be u plus 1 equals 0, and u minus 1 equals 0, right? But what was u? Let's just go a little bit further. If I divide both sides by 4 here, is it going to be u just to be 0? Okay, but what was u? Cosine. So I'm asking the question, when is cosine x equal to 0? Here it's going to be when is cosine of x equal to negative 1. So subtract that 1 from both sides, right? And this one here, this last one is going to be when is cosine x equal to 1. When is cosine x equal to 0? Pi over 2 and 3 pi over 2. When is cosine equal to negative 1? Pi. When is cosine equal to 1? 2 pi. 4 to 0, right? Okay. So, let's go back to this here. Okay. You told me x equals 0 should have been an answer. X equals 2 pi should be an answer. So those two graphs intersect there. You said x equals pi over 2. See, they intersect there, right? X equals 3 pi over 2. They intersect there, right? And the last one we haven't put in is x equals pi, and they intersect there. Okay? So that is the benefit of working down to just having 1x or 1 theta or 1 whatever as your argument for your trig functions. Okay? Because how they're going to play into some of our equations. This is, I've had students go away from my college classes, or I guess most situations is when I was teaching this for just advanced math, okay, and there wasn't roads attached to it. I'd have students always come back and say, I'm in trig right now, or I'm in calculus right now, and I need to solve this equation cosine x equals cosine 3x. And they're like, I don't have a triple angle rule. I don't know how to do this. I don't have the substitutions. There's multiple substitutions to go through to get there. Does that make sense? And now what sucks, and I did this for the last class, but we can maybe work through a little bit of this, is what happens when we're tasked with finding the cosine of 5x. Okay? Just think about all the work that's going to be involved here. Okay? You're now going to rewrite this as cosine. Now you go x plus 4x. But I think that's kind of silly based off what we just did. We just found what cosine of 3x was, right? So let's try to write this as cosine 3x plus 2x. And that's going to turn into cosine of 3x, cosine of 2x, and then minus sine of 3x, sine of 2x, okay. Cosine of 3x we just found, right? Cosine of 3x was 4 cosine cubed x minus 3 cosine x, right? Okay. Cosine 2x, well, we know that is the same thing as 2 cosine squared x minus 1, right? Okay. And like I said, you can use, maybe we're not interested, let's just get rid of that rule there, that additive task of writing things in terms of cosine. I'm trying to keep it as much as I can in cosine, but you could choose any one of the double angle formulas there for cosine if you want to, okay? Working through equations, you might find out that the one choice that you made doesn't make a whole lot of sense or isn't really nice, and you can then make a substitution later on that would actually undo that and put it into the correct substitution, okay? So it doesn't really matter. So that's that. All right, so we got that side taken care of. Now, we're going to go, I'm going to do this one first. So this would be minus 2 sine x cosine x, right? And then times sine of 3x. Now here's what stinks, and this is what stinks about having, 6x or 7x or 8x inside my argument. Because now you're going to get more of these. Now you got to depreciate that, right? So all this stuff stays the same. So I'm just going to, let me just highlight, so I don't have to keep rewriting all the same thing. Let me just highlight this. That's going to be part of what I use later. Let's kind of come over here and rewrite this thing here. So it's going to be minus 2 sine x cosine x times now sine of 3x looks like this, sine of 2x plus x. And now it's going to be minus 2 sine x cosine x. Now we go sine of 2x cosine x plus cosine 2x sine x, right? Okay, so it's going to be minus 2 sine x cosine x. This thing here turns into 2 sine x cosine x times this cosine x here, right? So let's just take care of that right now and square it. Okay, and this is going to be plus. Okay, let's go ahead and rewrite this as 2 cosine squared x minus 1 times that sine x. Okay. Can I, and I'm just going to do this real quick. Can I put that sine x through here? My tablet keeps dying. All right. So let's put that sine x there. So it would be sine x there, and then it was minus 1 times sine x, so it would be that, right? Okay. Now, can we, that thing there and that thing there are the same, right? So we have negative 2 sine x cosine x on the outside. We'll have 4 cosine squared x's, sine x's on the inside, minus sine x, right? Can I distribute this now? Okay. So we get what? Minus 8 cosine cubed x. I'll be taking that times that, right? We're going to have sine x times sine x, so it's going to be sine squared x. Okay, then it ends up being plus 2 sine squared x cosine x. We all good with that? Now, when I did this, I distributed that negative through here, right? So when I bring all this stuff down here, I don't have to, I just want to make sure I keep that as a positive. Okay? Now this stuff, can I FOIL that? The stuff that's yellow. All right, so I'm going to have 4 cosine cubed times 2 cosine squared. That becomes 8 cosine to the 5th, right? Now you'll have negative 3 times 2. So it'll be negative 6, but it's cosine cubed. And you have negative 4 cosine cubed, so that's going to be negative 10 cosine cubed. And then what? Plus 3 cosine x. And then minus this stuff, right? Okay, so I've got 8 cosine of the 5th x would be negative 18 cosine cubed x. So the positive 3 cosine x. Is that going to match up? Does it match up to anything? And now I have minus 8 cosine cubed x sine squared x plus 2 sine squared x cosine x. All right. Let's go a little bit further. Is sine squared the same thing as 1 minus cosine squared? think when we do that, you're going to find out 8 cosine of fifth x minus 18 cosine cubed x plus 3 cosine x. Now it's going to be what? Plus 8 cosine cubed x plus 8 cosine to the fifth x plus then 2 cosine x. I'm going to take this 2 and this cosine and use that as my monomial. And then what? Minus 2 cosine cubed x. Now, hopefully, if we did all this correctly. That was slow. Come on. There we go. All right, so this is going to end up looking, we have 8 cosine of the fifth plus 8 cosine of the fifth, so that's 16 cosine to the fifth x's, right? Those go away. We got 18 cosine cubed, 8 cosine cubed, negative 2 cosine cubed, right? So it's negative 12 cosine cubed. Negative 18, that'd be negative 10. Remove 2 more, so negative 12. And now we've got 5 cosine x's. And now think about how this, so let's just see if this is accurate. Let's see if we've made any mistakes. Hopefully not. Cosine 5x is that thing there. 16. Huh? I mess up?
Because that's negative 8 cosine x times third x. So where did you get the negative 18?
So I didn't, so, okay, so we went 8 cosine, so I had this here, right? And then 8 cosine of fifth minus, yeah, that should have been 10 there, right? 10 cosine cubed. Okay, so if that's 10, so it should be negative 4. Is that what we're saying here? Let's just see negative, so negative 4. So we have 16 cosine x. So this has to be raised to the fifth. Was it minus 4 cosine x to the third? And then plus 5 cosine. And we're wrong. All right, so all right, so I'll see what the error was. But the idea is, so you see how problematic that is, right? Okay, it's messy. Okay, I'm not going to make you do that. But listen, you don't know when you get to a calculus question whether that calculus question is going to have cosine 5x, and you need to be able to solve an equation that has it in there. Okay, now is that likely to happen? Probably not. Okay, but depending on where you go with this stuff, maybe it is. Okay, we're close. You see. And it's just, I think it's going to be a minor error that we've got going on there. But you see part of those graphs are mimicking each other, right? They're overlapping. So that's telling me visually that we're on to something there. We're pretty close. I'll double check and see where my error was. Okay?
I heard 18, and I was like, what is this?
You were selling the note.
I didn't say that. I'm sorry.
Where's the 18? But you said 18.
So this was 8 cos. So we brought all this stuff down, correct? This was all good. This was, So negative 8 cosine cubed sine squared, so that turned into, okay, so that should have been a 10, is what we're saying. And we took this negative, okay, that should be a minus there. Plus, okay, so I think that's, so it'd be negative 18, 8 cosine to fifth x minus 18 cosine cube x. So it does go to 16. 16, 16, negative 10, negative 8, negative, is it negative 20? Plus 2, so 16, negative 20, got it. Thank you, too.